Here we are at the last episode, and it's the one the whole topic has been building toward. We've walked each system on its own. Now we put them in a room together and make them get along. Up to now, we've mostly talked about the systems as if they lived separately, noting here and there how each one affects the architecture, how its space needs press on ours, but they also affect each other. Integrating everything a building carries all at once is what actually decides the building's performance. And compared with 20 or 30 years ago, this has become far more complicated. The technology is there, the control systems are there, the performance requirements keep climbing. More and more gets combined into a single unified whole, and what you want from that whole is for it to run without glitches. That's the objective in one sentence. All the systems must work together to enhance the building's overall performance, comfort, safety, and sustainability. And those demands aren't going to ease off. They're only going to grow. So the building has to work smoothly, or at least without major disruption. And when something does go wrong, there has to be a way to put it right fairly quickly. Let's make the stakes real with a few examples. Take civil. You're managing site utilities and water systems, and the environment is changing faster than our understanding of it, faster than our regulations, faster than our habits. So proper grading matters, and the stormwater has to be integrated with the site plan and the building footprint. Do we always do that well? Honestly, it's questionable. Sometimes we do a lot because it's mandated, and sometimes we do only the bare minimum the regulation demands. And poor civil design has real consequences. Water infiltrating basements, insurance claims rising, and an insurance industry strained to the point of nearly buckling, unable to meet the obligations it took on. People who believed they were covered discover it doesn't work out so easily. Then there are the physical conflicts, and this is the daily grind of coordination. Ductwork against conduits, against pipes, against beams, against chases, against vertical ventilation shafts. We'll be honest about how hard this is. A good part of a career can go into figuring out how a particular duct interferes with particular columns and beams on a big project, and it was never always obvious. For a long time, it was all done by hand, well before the software that's supposed to manage clashes for us. Closely related is the space problem. We start designing without giving proper due to the mechanical engineers and everyone else who needs room, and then we end up scrambling for huge mechanical spaces, electrical closets, sprinkler control rooms, elevator rooms. Code compliance is its own separate story on top of that, and the delays don't stop at construction. Some conflicts surface only while the building is in use, and those tend to become permanent problems. Because once a building is occupied, nobody quite feels obligated to fix the way two systems quarrel. Do the modern tools help? Building information modeling and clash detection do help, yes, but they're complicated systems to run in their own right, so they're not an instant fix. They're an aid, not a magic wand. Here's the professional anchor for all of it, and it comes straight from the chop. When you're integrating systems, follow the coordination checklists and recommendations in the CHOP to make sure the cross-coordination between disciplines actually gets done. And remember that on most projects, the architect acts as the prime consultant, which means the architect is the one responsible for seeing that all these disciplines are coordinated and properly integrated. That responsibility is a key thing to understand for the exam. Let's leave you with the kind of question that tests exactly this. Suppose you've got a mechanical system rated at 20 tons, and you're asked whether 300 or 400 ampere electrical panels would be enough. You'd choose 400 because the electrical engineer sizes the electrical system to the mechanical requirements and loads. Pick too small and you overload it. That's the whole game in miniature. The systems are connected, so you size one with the other in mind. It's fairly straightforward. Really, it just takes attention to detail, and that's coordinating engineering systems from the four core disciplines all the way to the work of weaving them into one building that performs. Thanks for spending the time with us across this topic. We'll catch you in the next one.